Okay, let us summarize what we have done so far in the physical layer first, before we start up with the next fresh topic. So this is what we have discussed in our previous sessions, and we have summarized each and every of these subtasks that the physical layer does. So when a transport block, or for that matter, it is the control information that comes from the MAC layer, what is the duty of the physical layer doing? Sorry, just hold on. So first it is taking care of attaching CRC. Then it is performing the segmentation of the code block uh, based on the sizes. If it is bigger sizes, it would be divided into pieces. And for each and every segment, going to attach individual CRC. Then go through the channel coding process and rate matching in order to map the amount of data available to the size of the resources that are in place. Then concatenate all the blocks together to form the code word. And then we have learned that there can be a maximum of 2 code words that we can have in 5GNR. Of course, if you wanted to generate 2 code words, so kind of you take 2 transport blocks at a time, and each transport block goes through the same process to get converted into a code word. Then a scrambling process takes place to scramble the data. So again, the scrambling mechanism is different for different channels and different mechanisms. Then modulation mapping. So depending on the modulation of that particular channel, so you might be implementing the corresponding modulation like BPSK, QPSK, etc. QPSK are your symbols will come out. Then we have learned about layer mapping. We have discussed the MIMO beamforming related things, and there is a maximum of up to 8 layers that we can have in 5GNR. So the data would be divided, the 2 code words would be divided in up to 8 layers, depending on, again, whether we are performing MIMO or, spatial multiplexing or whatever, depending on that, it would do the division. We learned that part in our earlier session. Then whatever the pre-coding matrix that is indicated from the receiving antenna in the form of, your channel information. So by using that, the pre-coding would take place. Then you start mapping the channels onto the resource elements. Finally, you generate the CP OFDM signal. And we have learned that if this is for the downlink and if it is for the uplink, between the modulation mapping and layer mapping, you have the DFT part. So to do the transform pre-coding in order to reduce the PAPR. Okay, so that is the extra step that would be present. So this is the overall process that we have completed learning, and each and every step we have concentrated and we did all that task. As of now, it is the time for us to enter into the channel concept itself and study how these channels would operate. And for each and every individual channel, what is going to be the changes in this particular process? As we have earlier studied, and even there's notes indicating here, not all the steps are going to be required for all the channels. And even if the steps are present, these step procedures are also not equal for all the channels. So now when we are going to introduce each individual channel, we would be studying which steps are actually required for that particular channel. And then even if a particular step is different for a particular channel, how it is different. So we are more or less interested in that. So we would be going through that when you are introducing those channels one by one. So let's get into the story. Now, we already got introduced to this concept of frequency domain and time domain. In frequency domain, we have these subcarriers, and in time domain, we have symbols, and you have the scheduling division done into slots, subframes, and radio frames, etc. Now, each and every element that you see here, each and every dot that you see here in this particular picture is called as a resource element, is one resource element. Now, we know that depending on that resource element, what modulation scheme that we are applying for that resource element, it can carry some amount of bits. That means that each resource element, if you have a resource element available with you, you can send the data. You can send data bits depending on the modulation scheme. So obviously, we don't have only a single type of data. We have various types of data, and all these types of data is typically we call it as channels. Now, definitely 3GPP, when they have proposed this frequency domain and time domain and all these are resources, they have to kind of do some kind of a segregation of all these resource elements and decide to allocate a particular resource element to particular channel, a particular type of data. Like normally we think about it, what is the best way to do the segregation of these resource elements into your channels? Normally, if I give you a chance, or if I take the chance for myself, I can decide the way that I like. For example, I can allocate the resources to different channels like this because I like this color coding. One color here basically represent one channel. So the blue color one is for one channel, and yellow color one is one channel, and so on. So I'm doing the reservation like this. Obviously, if I give you, you would color code it differently because you like different other colors, maybe. But color of the thing, it doesn't matter. But maybe if we say that we are totally sending like 10 types of data, so it is equal to 10 channels, and each channel will have to occupy some resource element somewhere in this particular frequency and time domain mechanism. If I give you the chance, you may color it differently. That means you are deciding the channels locations to be different. But here, whatever I design or you design doesn't matter. At the end of the day, what has been standardized. So typically what 3GPP does is they will perform a trial and error mechanism. So basically, when they wanted to decide and formulate this, they wanted to standardize this, they will actually conduct a lot of experiments. Okay, if you design it like this, what will be the effectiveness? What is the overall system effectiveness? So they will actually consider a lot of aspects, and they will finally decide with some particular pattern that, okay, so-and-so channel will go and take so-and-so position, and they finalize it and they standardize it. Now there are two problems. If the position of these channels related symbols, if they are kind of fixed, what you can do is you can code that information into software permanently. For example, like you can hard code it, and whenever the mobile equipment comes up, it will become very easy to find out which channel is where for the mobile equipment, because you kind of hard coded that information into the software. But sometimes what happens, or most of the times what happens, if they give that kind of hard coding, they kind of consider it as wastage of resources. You can't be flexible. If you wanted to change it for something else, you can't do it on the live node, live scenario. So they thought they wanted to keep it dynamic, and they wanted it to be configurable for the operators, at least in some cases, if not all. That means operator can decide, which kind of channel fits where and how much amount of resources it is going to take, depending on the configuration of the node. Here, the node in the sense G node B. Of course, mobiles will have to take the existing configuration as it is. They cannot command anything other than just demanding for the resources. So obviously, when a mobile comes up into the network, it will have to roam around and it will have to find out what's going on. Like in this particular time domain and frequency domain where my channels are. If I wanted to use a particular channel either for uplink direction or for downlink direction, where I have to use that channel, which resource elements I have to use for it. So mobile equipment will have to kind of find this out. Okay. One more issue I'll tell you. Normally, when a mobile equipment gets switched on in a cell, for example, mobile doesn't know where exactly it is getting switched on. It is not aware of that fact. For example, mobile may get switched on here or switched on here. When I'm talking about switched on, only time domain applies. Frequency domain doesn't. Just I'm talking from the time point of view. You may switch on at 9 o'clock, 31 minutes, 44 seconds, 44:55 milliseconds, or something else, some other time. Already this frame is running in the live environment. So what mobile need to do is where exactly it's switched on, it need to find out. For example, if mobile thinks that by switching on here, if mobile thinks that I have exactly switched on, at the starting of the frame, that is wrong. If mobile thinks that way, whatever the data it is getting from every channel that it's thinking that it is a channel is wrong. Sorry, my usual problem. Let's wait for it. So what mobile is supposed to do when it comes up? It'll have to perform something called as a synchronization. Find out what's going on, where exactly it is switched on. And maybe, for example, if you have the time domain divisions, let us suppose one frame and subframe, slot, etc., mobile need to find out where they are. All these frame and all this information, it need to find out. For example, one of your enemy has hit you on your head. You've gone into coma. You woke up after some number of days. You don't know either when you woke up. But when you looked at the clock, you see that the time is like 9:25, and immediately you won't say, hey, I have to now go and attend the class, attend this training, because it's 9:25 and 9:30 training starts. That's not the way it works. Why? You don't know when you woke up. It could be a Sunday, so you don't need to attend the training. Or it could be 10 years later. Now, training and all that doesn't matter at all. So, you have to sync up with the world. You have to find out what's going on. Is the clock showing morning or evening? You don't know in a hospital bed. You have to sync up with the world. Same way, this frame is getting transmitted 24/7 continuously. Every 10 milliseconds, once the radio frame number is changing, and mobile is in sleeping state, switched off. When mobile came up in a particular cell out of many cells, when he comes up, he doesn't know what's going on in that cell, where a frame is starting, where a frame is ending, where a subframe is starting, what is the frame number. Mobile know nothing. So first it need to kind of sync with this and find out exactly where it is located. It need to determine a lot of things about this frame structure itself. All that mechanism of determining the things related to this frame structure is what we call as synchronization, which every mobile equipment have to do. Doesn't matter like which technology mobile we are talking about. Even this synchronization mechanism is part of even old networks also, old technology networks as well. So how UE does this task? What is the UE's activity in a network? There is actually a complex mechanism. I'm not going to take you through all the complex mechanism at one stage itself. I will be introducing these in bits and pieces in different places. For today's relevance, so this is the way that I'm presenting the UE's activity. UE gets powered on. Normally, UE would have some amount of stored list of cells in its memory before it is switched off, if it is already an existing mobile. What mobile would try to do is, it will try to search for those cells from the list of cells that are stored. If it finds any of those cells, because it already know everything about that cell, what is that cell operating frequency and various other details, because it has stored that information related to the cell, at least the primary details, it has stored in its memory before it is switched off. So mobile will try to first find those cells. If those cells are found, well and good, it will go to this particular step somewhere here. What is that? We'll see. But if it could not find any cells, or if no cells are stored in its memory before it is switched, because it's a new mobile or you put a new SIM card, whatever. So in such cases, mobile equipment will have to do full band scan depending on its bands. Every device is associated with some bands. For example, if you purchase a mobile in India, that supports some number of bands. If you remember the list of bands that I have showed you in a big table, like we have concentrated on the N78 band that RIL is using, similar to that, a mobile can support multiple number of bands. Now, in all those bands, mobile would be looking for like which band cells I can find or which band frequencies I can find. So first it will measure the signal strength of every possible band it can find by scanning through the frequencies and find three best frequencies, three best bands that it can operate with. It'll find that out. And from that again, like in that, there might be many cells. It will be selecting, some cells on the basis of some RSSI threshold, received signal strength indicator, we call it as. So it is doing a cutoff. Which cells are under the threshold value of the mobile equipment's implemented mechanism and which cells are not within the threshold values. This is implementation basic, this RSSI threshold. But whatever the NR-AR-FCNs that mobile equipment found out that they are good, mobile will have to search for the SSBs on all those cells. What is the SSB? I will explain that. What is this NR-AR-FCN first of all? It is just a technical way of numbering all the available frequencies in the world and done by this NR technology. This AR-FCN is a concept that is existing from the old days, which is an intelligent way of numbering the frequencies. For example, when there is a frequency 3455 hertz, you don't want to keep it like that. You wanted to just give a number to it so that it becomes easy for mobile equipment to survive in the world with that number instead of the actual frequency value. But of course, there is definitely a mapping available internally. What the AR-FCN links to what frequency. Definitely, it is part of the software. So it's just a technical number. And on the cells that mobile found out good RSSI threshold, it will have to detect the SSBs, synchronization blocks, these are called as. And why? What does these synchronization blocks will help you with and how to detect them? All this is going to be the next best interesting part that we are going to see. Okay. So before even go to that SSB part, I would try to explain you one thing. This SSB comes under the common part of the cell usage. It is not related to the dedicated mechanism. What is dedicated common here? Dedicated typically represents one particular user related activity. We call it as dedicated. Common is for everybody. Now, we have discussed about this beam forming and the formed beams in our previous session. Now, if you have these dedicated channels and common channels, What way of implementing these beams is suitable for each one of these? For example, if you have to carry the data for dedicated channel, you can kind of create different beams for different data of different subscribers and send each beam in the direction towards that particular subscriber, which you can definitely do it. Because each and every dedicated beam here carrying the data that belongs to a particular subscriber, individual data. But no, you cannot create that many number of beams for common channels, which are carrying the common information, which it could be system and synchronization block that I'm talking about, or any other common channels that I'm talking about. You cannot create beams in all directions permanently and keep it like them for the purpose of making them accessible for the subscribers. Why not? Because you don't know where the subscribers end up being. If we have to create those many number of beams, you would be wasting the antenna elements. I've explained you that concept. In order to do beam forming, you have to waste the antenna elements. You cannot use it for MIMO or spatial multiplexing. We did see that in our earlier class. So, if you decide to keep these beams permanently throughout your diagonal, like in all directions, to help different subscribers who are popping up in different locations, you would be wasting a lot of antenna elements creating these many number of beams. So for common channels, sending the beams in all the directions all the time, because common channels are required for the mobiles all the times in a cell operation, at least for the new mobiles who are coming up, required to access these common data or common channels, which we are calling them as. What you have to do then? If you cannot create the beams in all directions and keep it. For example, if you did not do that, if any mobile comes up in a particular location that they can't read the common channel information. So the best idea is to do something called as beam sweeping with time. So that means this common channel data put into a beam, and by using whatever the antenna elements that you decided to use for that beam, you use that, and you keep on changing the beam direction. So in different time location, the beam would be pointing out to a different direction. So beam would be sweeping the entire all 360 degrees. It would be covering, so that any mobile that is coming up anywhere can read this common channels which are transmitted in the form of a beam at one point in time, in one particular point in time. You may not be able to read like every beam. You would be getting less signal strength from the other beams. For example, when the user is in one particular direction, only one beam, that particular beam would be suitable for you, not all the beams. So what they decided to do is allocate some kind of index to these beams and help the mobile equipment himself detect which beam is suitable for its operations. And that information will be useful at the later point in the time when mobile is dealing with various other things. How, we will see that later. But we can kind of send this common channel related information into these beams and sweep them throughout the 360 degrees of your of your geographical location in terms of direction. Okay. Now we have introduced this common channel called as SSB, synchronization signal block. So what is this, and why mobile equipment have to required to detect this synchronization signal block? I already gave you the problem statement. Mobile suddenly came up sometime in the cell, in the frame structure. It need to kind of detect where it is. So one way it can identify where it is with the help of this synchronization signal block. How this can help you? Okay. First of all, we discuss about mobile equipment's capability. When a mobile comes up into a 5G NR cell, what it can do is it can download some amount of frequency bandwidth and observe, get the carrier wave. From that, it can sniff all the time domain samples that we have discussed about, convert it into symbols, convert it into your I plus JQ symbols. Any mobile can do that. But the problem with what is the problem with the other channels and why we are using these special channels which are part of this synchronization signal block? All other channels except some special channels that are present in synchronization signal block would be using the modulation techniques that we have studied. What modulation techniques I'm talking about? QPSK, BPSK, etc., etc. So if the mobile equipment downloads any particular carrier bandwidth and decodes them, it will be getting all these, 1 by square root of 2, 1 by square root of 2 J symbols, all those symbols. But if a mobile equipment who is newly coming up, it cannot detect which symbols belongs to which channel. So if different channels are colored at different positions, mobile equipment cannot detect like which mobile equipment cannot detect all these symbols are carrying what channel data, because all the symbols look the same. They are all QPSK symbols or 16 QAM symbols or BPSK symbols, whatever, or 5 by 2 BPSK symbols and so on. Everything is a symbol. Everything is carrying digital data in it, but you cannot detect what the digital data is carrying. So they decided that we need some special modulation symbols in order to make themselves recognizable for the mobile. Mobile can easily segregate them, easily separate them. So in the list of channels that are present in this synchronization signal block, one particular channel called as this PSS, primary synchronization signal, is designed containing some special modulated symbols. We call it a Jadov-Chow modulation mechanism it uses. It is generated by using Jadov-Chow sequence. What is it? I'll show you. But these are not normal modulation symbols. So the idea behind this logic is, because the PSS is containing special modulated symbols and your mobile equipment is kind of capable of, decoding the carrier wave and converting it into symbols, from the decoded and converted symbols, your mobile equipment can easily detect if those symbols are actually processing these PSS symbols or not. It can easily detect that, because these PSS symbols are special symbols which are not following the general modulation scheme like QPSK scheme or 16 QAM scheme or 64 scams. Nothing. It is using its own modulation mechanism. It's using its own modulation symbols which are not part of general modulation. So you can easily detect where they are located. Okay, so why 3GPP designed mobile equipment need to read this system information signal block as the first activity? So they'll always keep this block of channels at one place, and there is a kind of an easy way of detecting this wherever it is located because of the specialness they have created for it. And 3GPP thought that, okay, if you can make this whole block identifiable for the mobile, after identifying it, we can kind of send information to the mobile, whatever the main details that are required in the system, we can send that so that mobile equipment will get its first impression of the network. So we'll give the first important details of the network as part of this system information block. That's the kind of idea here. And after performing a lot of trial and errors and experiments, they have decided that this way of designing this system synchronization system block or synchronization signal block would be perfect. They have decided that, because we have decided we are studying as it is part of our specification, as it is a standardized thing. And every 5G mobile in the world knows that this is a design of synchronization signal block, and every G-Node knows this. So it's a common knowledge. as they have standardized it. So what is this? What is the standard knowledge about the synchronization signal block? It must occupy in the frequency domain 240 subcarriers in total. In the time domain, it will have to occupy 4 OFDM symbols in time domain. So that's the kind of thing that they have put as like a box. 240 subcarriers, which is equal to 20 resource blocks, and 4 OFDM symbols. Wherever they have placed it, it doesn't matter. And again in that, they have created separate spacing for PSS and SSS and various different channels that can be present in it, called as PBCH, DMRS. What are they? We'll study one by one. So we have the PSS, SSS located somewhere in the middle, 127 subcarriers they are occupying, and those are numbered exactly. In total, we have 240 subcarriers. PSS must occupy which symbols, SSS must occupy which symbol. So in the time domain, the symbol position is 0 for PSS. So we have 4 symbols. So this kind of called as 0. This is 1, this is 2, this is 3. So in 0, we have PSS placed in these 127 symbol positions. Same way SSS. We don't care how they have decided the size to be only that precise, only 127 symbol. What is the logic behind it? The logic is all to do with the experiments that the 3GPP conducted. They must have taken different sizes. They must have tried it with even 255 subcarriers also, or only 100 subcarriers. They must have attempted every possible thing technically. They must have decided that this is perfectly suitable for us. They've decided. And again, in this blue color one, you can place 2 channels, PBCH and its own demodulation reference signal. The reference signal that will help demodulate this PBCH channel. But this demodulation reference signal related locations are variable. It is dependent on something called as a V value. That V value comes from the N cell ID, which is nothing but your PCI, physical cell ID, or we call it as cell scrambling code in general language. The values for this N cell ID are ranging from 0 to 1007. For every cell, operator is going to configure a different N cell ID, every cell. But operator also makes sure that none of the adjacent cells will have the same scrambling code or same N cell ID. They will try to make sure to have different N cell IDs, at least for the adjacent cells, in order to create some kind of an virtual difference. Especially this scrambling code or N cell ID is used in a lot of operations, which we'll see where it is used exactly in our coming up slides. We'll identify that. Okay, so this kind of a box tells us PSS, SSS are fixed positions. PBCH occupies all these symbols that are in the blue color, except the ones that are already occupied by PBCH DMRS. PBCH DMRS position itself is dependent on the V value. Okay, what do? I take an example to explain you this thing. Let us suppose we are going to consider this DMRS, the V value, the N cell ID value is 500. Now, in order to find out the V value, you have to divide the N cell ID by 4, modulo 4, which finds out the remainder is 0. So V value became 0. When V value became 0, DMRS symbol positions will be this. 0 plus V, V is gone. 4 plus V, which is 4. 8 plus V, which is 8. 236 plus V is 236. So you have again other places also in the second symbol position also, what positions it should take. Now, if you take a look at this right now, 4 different colors are explaining you 4 different things, as you can observe here. So what is the color coding? Dark blue color is PBCH, and we have this light blue is PBCH DMRS, These are zeros or null symbols, 0 plus 0j. We won't be placing anything there. We leave them empty. So there's kind of special modulation symbols, 0 plus 0j. SSS is in this yellow color and PSS is in this, dark brown. Okay, I did not put all the things because I cannot place 240 symbols in the slide set. So some things are not taken in the middle, as you can observe there with the number jumping, as you can see. So after 65, we jump to 173. The meaning is same pattern will continue. So these are your DMRS symbol positions. Sometimes they are placed in 3 symbols in time domain, sometimes only 2, because the middle one is already occupied by either null symbols or PSS, SSS or PSS. Okay. Now, one thing is very clear. This PBCA channel, which is present in the dark blue color, contains some data for sure. But in order to decode the data, you definitely know what is its position, the PBCH positions in this particular SSB block. If you cannot find out the position, you cannot decode it because everything goes wrong. All the information you think is the data is not your data. To detect the position of your PBCH channel, it is mandatory for you to detect the position of the PBCH DMRS. But that is only possible. This PBCH DMRS position identifying is only possible if you know something called as N cell ID or your cell scrambling code. Now I am kind of creating a dependency chart. Mobile don't want to get any. Mobile normally would like to get some information from the network, some crucial details. But to decode the details, there is a dependency right now, especially for this channel called as PBCH. As its location is dependent on this N cell ID indirectly. Okay, fine. Now, what is the data that is present in PSS? What is the data that is present in SSS? What is kind of data that is present in PBCH? And what is present in PBCH DMRS? All these channels, one by one, we have to see what kind of data they carry. And first of all, where this is placed, where this synchronization system block or signal block is placed, SSB block is placed. For example, if you this whole thing, I'm just going to convert it into a small picture, the one that you can see here. So just observe there, all the channels are present inside it, actually. As you can see, now this is the PSS, this is the SSS, this is carrying the PBCH plus PBCH DMRS. And these are the left out spaces, null symbols. This whole thing is the same thing that we have seen there, but it is right now placed in what? In your frame structure, in your resources. But where it is going to be placed? Is there any particular position for this SSB block? No, it can vary its position. You can place it at the middle of the band, operating band of the cell, or you can place it at the starting of the band. It is again decided by the operator where exactly they wanted to place this PBCH, or they wanted to place this SSB block. Now, the SSB is kind of repeated in multiple times, which each one is, we call it as a block. When multiple blocks are repeated together, we call that as a burst, which I will introduce it later. But this is a kind of repeating thing. This SSB block is in time domain. It repeat, not in frequency domain, but in time domain. It will repeat. Okay. Now we have to understand where this SSB placed. SSB is going to be placed by the operators. First, we are going to see this SSB placement in the time domain. And that is identified by this particular table that's provided in one of the specifications in by 3GPP. So you wanted to place the SSB for different bands, different subcarrier spacing and um, different bands. So there are some mathematical equations. On the basis of it, you can identify exactly in which positions, where exactly you can place your SSB. Only in these positions, you have to place the SSB. It's kind of mandatory. So time domain identifies the time domain symbols on the x-axis. So symbol position. For example, if you take the case of 15 kilohertz, it can be either present in 2 8 plus 14n. It depends on the n value now. If your operating bandwidth is less than 3 gigahertz, then you have to substitute n value as 0 one time, 1 as one time. That will tell you that the total number of opportunities that you have to carry your SSB block in time domain is 4. That is called as Lmax is equal to 4. This Lmax part, we will use it later. Please have a look at it. It is going to have dependency to some other channels which we study later. So here Lmax is 8 when the bandwidth is 3 gigahertz to 6 gigahertz. N value being 0, 1, 2, 3, and you are going to occupy these many symbols. Again, substitute these n values, each n value here in this formula. You get this. So Lmax became 8, Lmax 4, Lmax 8, Lmax 4, 8. But when you take higher bands, that's only present for FR2, FR21 or FR22. So after 6 gigahertz range, so case D, case E, F and G up to 960 kilohertz. So Lmax, how many number of times you can repeat your SSB block in a frame is these many, 64. Now we don't care about this 6 gigahertz part. We care about our RIL band. So our RIL band falls into this 30-30 part. 30 kilohertz. So either this is applicable or this is applicable. One of the two cases are applicable. So you have two different configurations. Of course, based on where mobile found out these SSB blocks, mobile can easily detect whether case B is followed or case C is followed, because you can observe the symbol positions are changing. Now, wherever these symbol positions we are talking about, remember there the special channel called as PSS is present. Any mobile can easily detect the PSS because of its special modulation. As it is containing special modulation symbols. So mobile can easily find out these positions where the SSB block is located repetitively in which symbol positions. Based on it, mobile kind of guess what case is operating in this network. And mobile also can detect Lmax, how many times it is getting repeated in a subframe. 4 times or 8 times, what is it? Mobile would be able to find that out. Because each SSB block contains that same mechanism, PSS, SSS, and all the other 2 channels, including the null arrangements. Okay. So if I take the 3 gigahertz to 6 gigahertz RIL specific example, you have 30 kilohertz subcarrier spacing. If this is the case B scenario, so these are the time domain symbol positions. So if you take a frame, I could not draw the entire frame. I have only taken 0, 1, 2 subframe. Second subframe is also middle. Only it is stopped in the middle. So only 2 subframes are kind of completed successfully, finished properly. So this gets repeated in these symbol positions, as you can see. In this particular subframes. So first one is 4, 0, 1, 2, 3, we have to leave. So you have 4, 8, 16, 20, and all that. So I'm noting down this. This is the 4 part. Similarly, if you take the subcarrier spacing for 30 kilohertz, and if you take a position here 2 into 2,8 kc, the change would be like this. Instead of this design, they would be little separated based on the change that is appearing here. So the operator decides exactly which one to take. Case B, case C, operator decides that. So the time domain position decided on the basis of the case decision. Of course, to only 30 megahertz, 30 kilohertz, we have this case decision to make. For all other things, it is kind of fixed. Now, where do we place this SSB in the frequency domain? In your subcarrier positions. For that also, 3GPP came up with this story, standardization. Your SSB middle part is called as SSREF. This SSREF should be placed exactly at a location that is suggested by the this particular table. For example, if you take this scenario, so you are starting with 3000 megahertz, which is 3 gigahertz block. Now you can kind of place your SSB block by taking this 1.44 megahertz as a reference point. What is this 1.44 megahertz? What is the significance of it? When mobile equipment is searching for this SSB in the frequency domain to detect where the SSB is placed, because mobile need to kind of search himself where it is located, where this SSB block is located. Every time in 3 gigahertz band, it would be filtering 1.44 megahertz subband. It will filter and it will decode all the symbols in that 1.44 megahertz. And from the decoded symbols, it would see if it can find out the SSB block or it is containing any PSS symbols or not in that 1.44 megahertz. That means search always would be conducted every 1.44 megahertz. For example, in India, 3300 megahertz band N78 is from 3300 megahertz to 3800 megahertz. You have. Now, different operators would get different bands. Now, let us assume that Jio got 200 megahertz band out of it. Now, for yourself, which band is operating in the present location you are in, and etc., mobile equipment may not be aware at least at the starting. So it kind of do the band sweeping. But how to search for it? You need to search piece by piece. So you cannot scan the entire frequency and decode all the symbols to see if the PSS is present in it, full band. Mobile cannot do that. Mobile will have to do piece by piece. So what is that piece is defined here? In case of low ranges, the piece of searching is very small size, 50 kilohertz only. If it is low bands, if it is high bands, it is even high, 17 megahertz. If it is FR2 case. So how much amount of band you will download and decode into symbols to search for PSS symbols? That is what is giving you that point there. So I put down some kind of a calculation. If we start with 3300 megahertz band, so there is some guard band up to 3300.86 megahertz or 860 kilohertz you leave out. And based on the number, based on this GSCN number, the first number that you can use, this GSCN number is nothing but every GSCN number is incremented by 1.44 megahertz. For example, if 3000 is called as GSCN number 7499, the next 1.44 megahertz is called as 7500. The next one is. So if you identify the GSCN, indirectly means you identify in which frequency band you found out this SSB, where exactly it is placed. Mobile would be able to recognize that, as it is searching subband wise, every 1.44 megahertz a piece. Okay, so for example, you can place what are the different possibilities for placing this SSB, as you can see it here in the SSREF. So you can place it at 7711 GSCN number, which corresponds to this bandwidth, and this is your SREF. exactly at SREF, we need to place your midpoint of the SSB. That is mandatory in our example. I put the same number there. So that means that you have to place your SSB by taking that SREF as middle. You have to place it above and below that. How much bandwidth is required for your SSB? It is 240 subcarriers or 20 resource blocks. So it is kind of, you can count it 240 into 30 megahertz. So you get 7.2 megahertz. So above you have to place 3.6 megahertz, below you have to place 3.6 megahertz on the basis of this point. Like this, by skipping every 1.44 megahertz, you will have a lot of opportunities in you. If you take your operating band is 100 megahertz, in that 100 megahertz, you will have a lot of opportunity to place this SSB. Now, operator kind of decides where to place it. Kind of, you can decide it to place at the starting. But of course, even at the starting, you cannot directly place at the starting. There are again some rules, as you have to leave out the guard band and some other little linked up things, which we don't require to discuss. But mostly it can be placed at the starting of the band to make it easily recognizable for the mobile, as mobile equipment will spend less time in searching for it. For example, if mobile knows that 3300 megahertz is the band starting, and it started scanning there, and in the first few 1.44 megahertz itself, if mobile detected the SSB, mobile don't need to do searching for this SSB for a lot longer time. If you place it in the middle or the top of the band, just because it is allowed, mobile will have to spend a lot of time to search for it. So typically it is the operator's decision, but 3GPP spec gives you the choice of moving around based on these numbers and calculations. Okay. So by following the rules that are set by 3GPP, you can decide where exactly you can place your SSB in time domain and frequency domain, depending on the operating band and various other conditions, as you just observed here. You have placed it, and mobile started scanning kind of 1.44 megahertz every time, and from that it is trying to find out 3.2 megahertz above, 3.2 megahertz below, try to see if it is containing the PSS symbols in that particular position. But how mobile can detect these PSS symbols? What is the speciality of these PSS symbols? What kind of data it carries? This PSS carries. So that is the next topic that we are going into. So these PSS symbols are calculated with this sequence. Sorry, I made a mistake of telling you that it is Jadavcho symbols. It is not. For LTE, it is Jadavcho. For 5G NR, it is not. Sorry. So the PSS symbols are calculated with this equation, 1 minus 2x of m. Now, what is this x of m here? The x of m is defined here with this equation. As you can see, m value varies. I will explain that concept. But this m value is dependent on the NID2 value. This NID2 is also called as sector ID, whose range is 0, 1, or 2, the sector ID. It is configured by the operator. And it is going to be different in different scenarios, different PSS, different cells in different places. It is going to be a different value. This sector ID is. Now, how many different PSS signals that are present in 5G network? Only 3 different possibilities. Those are here by substituting in this particular part. How to calculate this PSS? Assume that the NID value is already configured, either 0 or 1 or 2. Let us assume that it is 0. So that makes it M is equal to N, because NID2 doesn't matter now. Now, how to find out this X of M? Because in order to calculate this value, you need X of M value. What is X of M? X of M is defined as X of I plus 7 is equal to X of I plus 4 plus X of I modulo 2. That means if you wanted to find out X of 7, you have to define that as X of 0 plus 7, which turns out to be X of I value presently is 0 because we have considered 0 in this I position. So 0 plus 4 is X of 4 plus this is X of I, which is X of 0. Modulo 2. Now this X of 4 and X of 0 are already identified. X of 4 value is 1 and the X of 0 value is 0. So the bottom order elements are already defined. Only from the 7th element onwards, you need to find out the values by using these pre-order elements. So by substituting them, so X of 0, 4, X of 4 is 1, it is fixed. X of 0 is 0, substitute, you get a value 1. 1 modulo 2 is 1. So 7th bit is 1. For 8th bit, you have to place 1 in the 8th position. That's it, simple. You can kind of repeat it. How many times you have to repeat this operation? Already 7 values are available. You have to repeat this operation another 120 times because PSS is occupying 127 symbols ranging from 0 to 126. These are 127 symbols. To place into 127 symbols, we need 127 bits. Each bit is going to be turned out to be either 1 or minus 1. Because this X of M, as we are doing it with modulo 2 always will give you the output either 0 or 1. No, nothing else. If you divide any number with the 2, you get a reminder either 0 or 1. If you substitute 0 or 1 here, when the X of M element value is 0, it becomes just 1 because this whole part becomes 0. But when X of M is 1, it kind of becomes minus 2. 1 minus 2 becomes minus 1. So that is why the total combinations that you see here, the bits that you have to send on the PSS is the combinations of ones and minus ones. So these are 127 ones and minus ones. Remember, ones and minus ones on our constellation diagram are definitely special symbols. 1 is kind of identified as 1 plus 0j. So your imaginary part is 0. Minus 1 is identified as minus 1 plus 0j, which is at 180 degrees phase. So this is at 0 degrees and this is at 180 degrees. And these two phases, we are not using any other modulation symbols. In QPSK or 16 QAM or anything else, definitely we have some theta in other modulations. In BPSK, we are using 45 degrees and 225 degrees symbols. In QPSK, we are using 45 degrees, 135 degrees, 225, 315 degrees theta value, the angular modulation. Here we don't have, angular. Almost it is on the x-axis because real parts are 0 in these special symbols. Because these are specially modulated symbols, it will become easy for the mobile equipment to detect them wherever they are located. So once the mobile equipment scans 1.44 megahertz midpoint, go there and above 3.2 megahertz, below 3.2 megahertz, it will decode the symbols and decode them and try to see if there are PSS symbols present in it or not. If PSS symbols are present in it, mobile will look at the second thing. Hey, which package is present? This one is present, or this one is present, or this one is present. Mobile will look. If mobile found this, mobile immediately detect that the NID value configured by the operator is 0. If mobile finds this, it finds out that NID value is 1. If it finds this sequence, mobile will find out that the NID value is 2. So mobile is detecting the NID value. So not only this PSS helping the mobile equipment to detect itself, easily detectable, on top of that, it is also intelligently giving one information to the mobile called as NID2 or sector hiding. Is this clear? Any questions in this PSS part? Now, once mobile found out the PSS, mobile kind of come to a some sort of a frequency sync. At least it will know that which is the operating band over here, even if it is doesn't know everything else. In the time part also, it will kind of start getting a sense. Hey, either I must have been one of those symbol positions. I'm not sure. But mobile will try to find out how many more SSB blocks. It need to find out more SSB blocks to see what is the SSB block pattern that is present in this cell. Mobile can do that. But mobile kind of try to find out what is the NID value from this PSS. What is the use of this NID value? Why they are indirectly coding that NID value into this data? We'll find that out little later. But definitely this NID2 value is useful for mobile for performing further operations. All right. Next. So the next one we have is the secondary synchronization signal, which is placed in the second symbol position. PSS is placed in 0th symbol position, 127 middle carriers. But SSS is placed a little later, other side. But once mobile detected PSS, mobile can easily detect SSS. It's not a big deal because they're co-located. They are all part of one block, and the positions are known to every mobile software. How the DSS is generated? Generated with these X0 sequence and X1 sequence. And again, in turn, this X0 sequence and X1 sequence can kind of take based on this M0 and M1, which have been derived here. Now, M0 is containing two factors, NID1 and NID2. NID2 is the sector ID that goes in one of the inputs. Okay, that means if mobile wanted to decode the synchronization signal that it is receiving PSS position, mobile must have already completed decoding PSS. So they have created kind of linking. Why? Because you cannot decode SSS if you don't know what is the NID2 value. NID2 can be either 0 or 1 or 2. But we have to see it from the transmission point of view, reception point of view. Transmitter is G node B, receiver is the mobile. First, we will concentrate from the transmitter point of view, G node B point of view. So G node B need to kind of calculate this SSS sequence. And whatever the data that is generated, it need to send the data to the mobile in that particular SSS symbol positions, 127 symbol positions. So how it does that? So there is a NID1, which is called as a group ID, whose value range is from some 0 to 336. It is configurable again by the operator, this NID1 value. .336 values are possible for NID1. Operator will configure one value there for every cell. So once that NID1 is configured, the transmitter, which is the G node B, stuffs in the NID2 that is already configured, NID1 configured, calculates M0, and with the NID1 itself, it calculates M1. Once you have M0 and M1, substitute them over here, you can now calculate X0 sequence and X1 sequence. The equations that are defined here as same concept. X0 of I plus 7 is defined like this. X1 of I plus 7 is defined this way. So you have two equations for calculating X0, X1 sequences, and their pre-order positions are already identified. So for the first 7 positions already valued at zeros and ones. So if you want to calculate the X0 of 7th element based on the M0 that you are substituting, so 7th element, you define it as X0 of 0 plus 7. You place 0 in this position and this position. X0 of 4 is already defined in this box. So you take the value as 0, you take the value X1 of 4 also as 0, if you take it in X1 case also. So you keep doing the substitutions. That's it from these already pre-ordered elements that are available. And GNodeB can calculate the SSS sequence. Easy as that. So it works on operator configuration. But we have to look at this from the receiving point of view, that the mobile equipment point of view. How it is advantageous from the mobile equipment point of view. Mobile detected the PSS. From that, it extracted NID2. Now, mobile will decode these SSS symbols because it already know the position of the SSS symbols. It decodes them. Now, after decoding, mobile would have to, whatever the sequence of data that it has received, that sequence of data, by taking it as available data, mobile will have to solve the mathematical equations to find out what exactly is the NID1 value that they have used in it. Mobile need to find it out, because in the mathematics, these formulas and all, everything is known to the mobile. This X0 sequence, X1 sequence are known to the mobile. So data is received. Now, for the kind of data you have received on SSS, what NID value is possible? Only one value would have been possible. Every time you change the NID value, the total sequence would change. Total sequence is different. So there are 336 different sequences possible with 336 different NID values. So based on the sequence that the mobile found out, mobile guesses what is the NID1 value. It would guess from the mathematics, reverse engineering, because I already knew the formulas. If this data need to be this, what NID value that the transmitter has used, GNodeB has used. So from that, you would detect this NID1. Also, this SSS channel will give the initial power estimate for the operating cell. In whichever cell mobile is syncing right now with, in that cell, it will get the initial power estimation, which we'll see a little bit more on it little later. But first I have identified that task there. Initial power estimation. It will find out the RSRP, RSRQ values of this SSS, the mobile. It will sift the signal strength, find out if the signal strength is good or bad for its operation. Or at least it will sift and find out. Why it is, first of all, finding out this power value. You remember, if mobile equipment found out multiple cells, I told that for every cell, mobile need to kind of detect the SSB. Mobile might have detected multiple SSBs, belongs to multiple cells. Now, out of all these cells, mobile need to find out, or mobile need to kind of select in which cell it is going to operate. For that cell selection, so these power values, that the power that mobile estimated on these SSS symbols would be useful. Of course, if the mobile equipment is near to a cell, the signal strength would be little better. Otherwise, it is little low. Okay. So mobile already estimated NID2 from the PSS. Mobile estimated NID1 from this SSS data that is received. And what does the mobile do with both these numbers that it has calculated, NID1 and NID2 that are estimated? It will substitute these two numbers it found out in this formula to calculate N cell ID. This formula is fixed, known to every mobile equipment in the world. Every 5G mobile in the world knows this formula. 3 into NID1 plus NID2. NID1 values would be ranging from 0 to 335. Based on what sequence you have received, you calculate NID1 value from SSS. And based on one of the three possible PSS symbols, you calculate NID2. So substitute these numbers into that formula, you get a value ranging from 0 to 1007 maximum. If you substitute both zeros, it will become 0. N cell ID is 0. If you substitute the maximum numbers, 335 and 2, into these fields, you get 1007. So the total N cell IDs are scrambling codes for a 5G NR cell is 1008 values. And this physical cell ID, PCI, or N cell ID, or simply call it a scrambling code. is important for mobile equipment to access all other channels. Why? Because all other channels data except PSS and SSS is scrambled with this scrambling code. And don't directly, we cannot scramble it with the scrambling code. This scrambling code is used in calculating a scrambling sequence. That scrambling sequence is used to scramble the data of the other channels. So if mobile equipment want to decode any other channels except PSS and SSS, mobile definitely need this PCI. Without PCI, you cannot decode them. You cannot decode any of them, for that matter, any other channel. Only the two channels you can aramse decode without having this PCI is PSS, SSS itself, because you are identifying the PCI from them only, from these channels data itself. You are identifying that. Okay. Now let us summarize. Mobile equipment somehow can easily detect this system synchronization block because there are some special symbols placed, which are special modulated symbols, works on 0 degrees, 180 degrees mechanism, which no other channels would use. So they are easily detectable when you are, scanning through the frequency and decoding 7.2 megahertz subband every time. If you take 30 megahertz is your operating band. So from that, mobile estimated this PCI. So this PCI is kind of giving the thing to as a next step to the subscriber. Mobile can do in the next step by using this PCI. We'll find that. But I already told you about this. Multiple blocks put together. These are called as SS burst. And SS burst would be decided based on the configuration. Of course, configuration is not fixed. Configuration is variable. Operator can decide to send all the SS blocks in a burst, or some of the SS blocks can be ignored as well. So there is a concept called as a bitmap also. By using the bitmap, you can ignore some of the these SS blocks, SSB blocks. I'm not going into those details because mostly bitmap is used for your non-standalone case, not for standalone. We don't use it much. So standalone, it is not required. Non-standalone case, that bitmap works. But I'm not kind of telling you that. Simply, it is decided by the operator's configuration, what operating bandwidth and subband and where you have placed and so on. I have already told you that thing earlier. But how the logic works in reality? So after mobile equipment detecting these blocks in these positions one by one, once mobile detected a block in the frequency domain, mobile kind of can try to detect the blocks in the time domain continuously, at every gap, and try to measure the signal strength of SSS and find out which which block is giving you good signal strength. Now, if a particular block is giving you good signal strength, now you are in the direction of that particular beam. So each SSB block is getting transmitted in the direction of your beam. So mobile, by detecting this signal strength, identifies which block is better. For example, if you take that aqua color one and yellow color mobile phones, so by assuming that they are starting here, signal strength point of view, so the signal strength of that beam is little there but not too high. But this beam signal strength is good. For example, when you are reading SS block 1, you got good signal strength. But when you read SS block 2, this aqua color mobile picked up the highest signal strength among the other SSBs as well. So as you keep going in this circle, because these beams are all the other way around completely, definitely mobile would be getting less signal strength on them. So signal strength keeps reducing. So mobile would detect that, okay, this beam is operable for me. This is giving me the highest signal strength. Same for mobile 2, story would be different. For him, SSB block maybe 4 would be good. This is like 0, 1, 2, 3, 4, 5. SSB block 5 is good for the mobile. That is where it is getting the highest signal strength when it has measured the symbols in the SSS. Now, all these blocks are numbered. So these block numbers are going to be provided to the mobile intelligently inside. The information would be provided inside. How this information is kind of conveyed to the mobile? This block numbers, the SS burst numbers are block numbers. Let us look into that aspect. Okay. The next channel we are discussing to understand how mobile gets this block number, SS block number, is PBCH DMRS. Stands for Physical Broadcasting Channel. DMRS is demodulation reference signal. So basically, this is kind of a reference signal. Okay, how this reference signal mechanism works? Let us see. The reference signal equation for DMRS is this: 1 by square root of 2, 1 minus 2 into C of 2m plus 1, j 1 by square root of 2, 1 minus 2 of C in m plus 1, 2m plus 1. I will try to break this down at multiple levels and try to explain you what's going on here. Normally, the C of 2m plus 1 or C of 2m, these are scrambling sequences. The C of n is, whatever the scrambling sequence values you get is going to be either 0 or 1 of the two, any scrambling bit. You are taking a scrambling bit present in 2m's position. You are taking a scrambling bit present in 2m plus 1 symbol position or 2m plus 1 length position. But the scrambling bits are always going to be 0 or 1. If you substitute 0, this whole term will become 0. Because if you find out that the C of 2m, wherever it is, if it is 0, this whole thing becomes 0. You have 1 minus 0. So 1 minus 0 is 1, it becomes 1 by square root of 2. Similarly, if C of 2m plus 1 also is substituted as 0, this becomes 1 by square root of 2j. So 1 by square root of 2 plus 1 by square root of 2j when you substituted when you have substituted 0 both the locations. But you found out that this is 0 and this is 1. Then what happens is when this entity becomes 1, 2 into 1 is 2, 1 minus 2 is minus 1. When it is minus 1 is multiplied with this thing, so this whole part will become minus instead of plus. So you have minus 1 by square root of 2j instead of plus 1 by square root of 2j. Similarly, if you place 1 here also, this can also become minus. So total possibilities are 4 in these, whatever the symbols that we generate for PBCH DMRS, there are 4 possibilities, which is plus 1 by square root of 2, plus or minus 1 by square root of 2, plus or minus 1 by square root of 2j. Any one of these. These things, we already know that these are QPSK symbols. Quadrature phase shift keying symbols, these are. So that means what you transmit as DMRS symbols is QPSK symbols itself. But these QPSK symbols are not generated from the data. They are generated from the scrambling sequence. The scrambling sequence plays the important role here. C of n is the scrambling sequence. What is the scrambling sequence? Yeah, in our previous session, we have introduced this scrambling sequence, but we did not have the time to go through that entirely. So we kind of skipped it through. We'll go back. So this is the scrambling sequence equation. If you wanted to find out the scrambling sequence, you need to have x1 sequence and x2 sequence, two mathematical equations, mathematical sequences. X1 sequence is computed with this by knowing the pre-order values, by substituting the pre-order values. First 31 values are already identified. You substitute them and you get any number of x1 numbers, any x1 values. If you want to find out x2, x2 equation is dependent on this. But for x2, first 31 values are going to be dependent on the C init value. I have explained to you in the previous class, the C init value is kind of different for different applications. The C init value. Now, if the application changes, application here typically represents a channel. If the channel changes, the C init value would change. Now, once the C init changes, the first 31 values of X2 sequence would be changed. If first 31 values are changed, after 31, if you wanted to find out X2 sequence values, you have to apply it into this formula. N plus 31, you define N as 0. So it becomes X2 of 0 plus 3, which is X2 of 3, third element value, X2 of 2, X2 of 1, X2 of 0. So the pre-order substitution again. Whatever the available elements you have, you are substituting them to calculate higher level element value. Simple mathematics. If you wanted to find out x2 of 32, for example, you define it as 1 plus 31. So what will happen here? In the n position, you have to place 1. So what will become? X2 of 4, X2 of 3, X2 of 2, X2 of 1. Because already first 31 values are available. So you take those element values and substitute them over here. So the first 31 values is dependent on the C init value. Okay, great. Now let us go back to our calculation. What is the C init that is applicable for this channel? Remember, for every channel, calculating scrambling sequence, to decode the data of the channel, you need the scrambling sequence because data is scrambled with the scrambling sequence. To calculate it, you need the C init value for that channel. Now, for this channel, for this PBCH DMRS, the scrambling sequence is the one that is listed here. 2 power 11 into I bar SSB plus 1 into floating value of N cell ID by 4 plus 1 plus 2 to the power of 6 I bar SSB plus 1 plus N cell ID modulo 4. Now, G node B can easily calculate this because G node B knows the things, obviously. So we have to look every channel from the transmitter point of view, receiver point of view. First, we look at this channel from the transmitter point of view. What do we understand if you look at it from the transmitter point of view? From G node B point of view, how G node B knows these fields? N cell ID is configured by the operator, which is the physical cell ID. Every cell, physical cell ID is going to be different. Operator configurable. Just now I told you that the value range is from 0 to 1007. One of these 1008 values would be configured for every cell. So you take multiple cells here. If operator configured 524 as the N cell ID of this cell, operator configures 5 as the N cell ID here, 29 as the L cell ID here, 894 as the N cell ID here, 755, 492. So for all adjacent cells, you will configure different N cell ID. That's the kind of operating rule. So substitute that N cell ID. Now you can have the C init value, but there is one more field here, which is I bar SSB. What is it? So this I bar SSB is different for Lmax 4 or Lmax greater than 4. You remember the Lmax from our SS block transmissions? How many times your SS blocks are getting transmitted? 4 times, 8 times, 64 times. For different configurations, different things is there. So they are kind of keeping that number of times you are placing this SSB block. Based on that, they are identifying this I bar SSB, L bar SSB value. Okay, how it is defined as LRI, whatever. Actually, it is I bar, but it is being shown as L. So how do you calculate this L bar SSB? Whatever the thing that you need to substitute. Because in order to generate this sequence, you need CINIT value. If you know CINIT, you know the X2 sequence values. X1 is fixed. X1 is kind of constant. X2 sequence only known with CINIT value. Okay. So this I bar SSB or L bar SSB is equal to ISSB plus 4 into NHF. Here, this NHF is the number of the half frame in which the PBCH is getting transmitted, or basically your SSB block is getting transmitted in the first half of the radio frame or second half of the radio frame, where it is placed. That will tell this NHF value. If you are transmitting the SSB in the first half, you will put 0 value. Otherwise, you will put value 1 in the second half of the frame. These are called as half frames. I told you this in earlier class. Your frame is divided into 2 halves. First half frame 0, half frame 1. That depending on that, NHF value would be decided. Where are we transmitting this DMRS? Because we are now considering from the transmitter point of view. Now, ISSB is the 2 least significant bits of the SSPBCH block index number. What is the meaning of 2 least significant bits of the block index? First of all, what is this block index? SSB block index. The SSB block index is nothing but the block transmission numbers that we have used, that we have seen in the table. For example, the block index can be 44. So in case if the KC 30 kilohertz, if we are transmitting the DMRS for this 44th element block, so we can kind of say that 44th element block, we are, we are transmitting the DMRS. So now, what is the least significant bits of this 44? You have to convert that into binary in order to find out the least significant bits. So you take programmer calculator 44. In binary, you have this value, but least significant bits, 2 bits are 0, 0. If it is 3 bits for any reason, it is 100. If it is 2 bits, it is 0, 0. 3 bits, 100. So whatever is the index number, that index number kind of get converted into binary, and from that binary bit, last 2 bits would be taken as the ISSB value. So substitute ISSB and NHF value as either 0 or 1, depending on whether it is getting transmitted in first or second frame, and calculate this I bar SSB if it is Lmax 4. If it is Lmax greater than 4, I bar SSB is equal to ISSB directly. But in this case, the ISSB is taken from 3 last significant bits or least significant bits from the SSPBCH block index number. So convert that number into binary, take the last 3 bits. Those 3 bits will become I bar SSB if Lmax is greater than 4. If it is greater than 4 means all other cases, 8, 64 case we are talking about. But if it is equal to 4, you need this NHF also, first half or second half of the frame. No, so place these values in here, calculate the CINIT. Once the CINIT is available, mobile can generate the scrambling sequence. How? It takes the CINIT value and expand it with this equation. You will be able to find out the first 31 values, 0 to 31 values you can find out. And by using the first 31 values of the X2 sequence, by doing the pre-order substitution, you can calculate any number of X2 values. It's possible. And then you generate X1 also. X1 is fixed. X1 first 31 values are fixed. So you can generate any number of X1 values. Substitute X1 and X2 sequence elements values here. You get C of N, the scrambling sequence that is needed. And once you have the scrambling sequence, you take those scrambling sequence bits, zeros and ones, and you substitute those scrambling sequence bits in this particular place. Once you place them here, you get your PBCH DMRS signal that is generated. That is from the transmitter point of view. By taking the transmitter as gene will be here. What about the receiver point of view? Receiver knows this formula. Now, what is the duty of the receiver is, after receiving this PBCH DMRS bits, receiver must be able to estimate what is the ISSB value, 2 or 3 least significant bits that are of the PBCH block index number. It is getting half of the block index number from here. Not entire thing, only half it is getting from here. And mobile also will be able to identify right now whatever the SSB block it is downloaded, in that SSB block is present in first half frame or second half frame. You can identify that. Because if the mobile receives, because mobile knows all these mathematics, mobile received some symbols are nothing but your PBCH DMRS bits. By analyzing the PBCH DMRS bits mathematically, mobile can definitely identify what is the I-bar SSB value used in it. NCell ID is already known to the mobile. You remember, mobile calculated this NCell ID from the PSS and SSS operation already by using the bits that it has downloaded in PSS and SSS. It calculated that NCell ID. So mobile knew NCell ID. Only factor that mobile equipment doesn't know in this is I-bar SSB from the received data. So mobile can easily estimate by doing just absolutely reverse mathematics. What is the I-bar SSB value? From that I-bar SSB, mobile will be able to estimate what is the ISSB value and what is NHF value, whether it is the first half or second half. It will be able to figure it out, figure those numbers from the mathematics. So the data, this PBCH DMRS data, is kind of giving some additional information to the mobile, like 2 additional details, like what is the SS PBCH block index, half part, not even half, 2 or 3 bits, least bits you get, and what is the frame you are operating on, which half frame right now you are in. So mobile kind of can detect it. Now I'll show you this, these 3 things which I have showed you so far in the simulation, so that we'll have clarity on it. First, I'm going to show you, okay. First, let me show you PSS. So PSS, we are seeding the NID value either 0, 1 or 2. By using that NID value, you can kind of calculate remaining thing. First, you are finding out the X values. Okay, X values that you are initializing, the X that you are using. So they've become 127 X values from the first 7 values available. By substituting it in this formula, by running it in a loop 120 times, I'll be able to find out another 120 bits, totally 127 bits. First time I'm seeding value 0 for NID2. When we seeded 0, with that, what is the PSS generated? These ones and minus ones. If you seed 1, so then these ones and minus ones, the combination is different. Here we have 3 ones at the starting. Here it is 1 minus 1 minus 1. So they are different. So every time you substitute different NID value into this formula, the M values will be changing. And when M value changes, the DSS output would be different. So here it is minus 1, minus 1, minus 1. So one of these 3 sequences. So if you have to draw it on the constellation diagram, either it is positive 1 or negative 1, plus 1.0J, minus 1.0J, PSS. SSS is so again you calculated X sequence here also, and you are calculating X0 sequence which is 127 bits, X1 sequence which is 127 bits, because we have 2 equations in SSS case, X0 sequence, X1 sequence. And then you are seeding NID1 and NID2 because both are used for SSS transmission. I'm configuring 100 for NID1 and 1 for NID2. So they will kind of go in NID values that we are seeding that will find out these M0 and M1 outputs. From that M0 and M1, by substituting M0, M1 in their respective positions, you would calculate the DSSS. So you get this. And if you would draw the DSSS, even this also is special symbols containing only ones and minus ones. Either the symbols are in the constellation present on the right hand side of the origin or left hand side of the origin without any angle, 0 degrees or 180 degrees if you take the constellation. And from that you can calculate, NID, which turned out to be 301 if you substitute those NID values respectively, NID1 and NID2. For example, if you change, everything changes. If I'm seeding differently, if I'm rerunning this, sorry. It is asking me to input NID1 and NID2. I'm choosing NID1 value is going to be like 335 and NID2 value is set to 2. And now this is my SST sequence. On the constellation diagram, these are ones and minus ones only. But from the received thing, you can calculate. So the biggest NID value that is possible is 1007. Okay, now this NID value or N cell ID, we are calling it as, is being used in all other channel operations, including PBCH DMRS that we have here. So how the PBCH DMRS is working out? Now I can consider L bar max. L bar max possible inputs are 4, 8, and 64 from the table, if you remember L max. So I'm seeding what? 4 in this case. I'm configuring N cell ID value as 500. NHF, I'm taking it as the first half, 0. In this example, of course, you can run it with the same, with different other details. You can change them, inputs, your wish. ISSB, in what block number? I have taken only 30 kilohertz case. So in one of these blocks, the DMRS is getting transmitted. PBCH DMRS is getting transmitted. Okay. So now once all the inputs are provided, these are the inputs that I have provided that have been displayed here. Now we are calculating ISSB in binary format, and I'm going to take either the first 2 bits or 3 bits. I'm going to take and converting it into decimal value. Actually, here I have to take 3 bits. I did not repeat it. So this should be defined as 3 bits. I copy pasted, but forgot to modify that. Anyway, we did not use the first frame. Our 30 megahertz, 30 kilohertz, we don't need this 3-bit part because that is applicable only for LMAX greater than 4. Of course, it is applicable. 8 case is there. It is needed. Anyhow, corrected that. But anyway, we did not use that value in our calculation. So depending on it, we are determining the L bar value. Now, what is the size of the DMRS you have to calculate? DMRS is going to take exactly 84 symbol positions. How do I know? That I know from the table that I have showed you at the time introducing this SSB block. So in this SSB block, it is clearly explained PBCH is going to be occupied in how many symbol positions. PBCH DMRS is occupying how many symbol positions. Now I have counted all these symbol positions and found out that it is that number that I have taken as the input there, 84. So that means that we need to generate your PBCH DMRS sequence as 84 symbols, 84 QPSK symbols. But to generate 84 symbols, we require a scrambling sequence double that of size. That means if you wanted to calculate this M being 84, You require a scrambling sequence double of that size, because for calculating every DMRS bit, you require 2 bits of the scrambling sequence. C2 of m bit, C2 of m plus 1. For example, if you substitute, if you wanted to calculate the PBCH first bit or 0th bit, you substitute 0 there. So it becomes C of 0. You need C of 0 bit, scrambling sequence 0th bit. 0 plus 1, this is C of 1. So you require 2 bits from the scrambling sequence to calculate 1 bit of the DMRS. For example, if you want to calculate R of 5, what it becomes? So this becomes C of 10, this becomes C of 11. So you require again 2 bits. Like that, if you want to calculate the last one, R of 83, that is the last one, 84 bits and numbering from 0 to 83. So C of 2m. So you require scrambling sequence up to C of 83 into 2. So it is 166 you require, and C of 167 you need here, plus 1. So basically, from C of 0 to C of 167, there are 168 values you need. That is exactly the double of this number of symbols that you have to generate. So double that of size. So I'm considering m as of the double, 168. So I'm calculating the x1 and x2 sequences. X1, the first 30 values are already prefixed, and I have generated the needed x1 sequence values. So actually, you require x1 sequence 1768 values. What is that 1768 came from? First 1600 values, you won't use them. It is a kind of fixed in the scrambling. Only the last 168 values you have calculated, you will use as your scrambling bits. That means first 1600 is kind of waste. You will throw them. That means if you require a scrambling sequence of size 168, you need to calculate 168 plus 1600. If you need a scrambling sequence of size 400, you need to calculate 1600 plus 400, 2000 scrambling bits you have to calculate. Only last 400 bits you will use them. First 1600, you throw them into dustbin. You won't use them for your operation. Why is that? What is the logic behind it? That logic is in the scrambling sequence itself. So if I take you back to the scrambling sequence, so you have used this NC value as 1600 here. That means that in the X2 sequence, even if you substitute, if you want first scrambling bit 0, if you substitute 0 here, but NC is 1600. That means that you are starting with the 1600th bit of X2 sequence, 1600th bit of X1 sequence. So by taking those bits, by combining them, you are performing modulo 2 operation. The remainder will give you the scrambling bit. Of course, the possible scrambling bits are going to be 0 and 1, because X1 sequence and X2 sequence are zeros and ones. So if you combine 0, 0, it will become 0. 0, 1, 1, 1, 0, 1. If it is 1, 1, 0, it is like that. Only 4 combinations you can get. But because we kind of use that NC there, we require X1 sequence, NC plus the number of bits that we want to compute. Because we want to compute scrambling sequence of size 168, we need the X1 sequence from 0 to 1768. Same way X2 from 0 to 1768. We need these sequences up to that size. That's why we did that calculation here in this place. The length is that many elements we found out. Same way, now you have to find out X2 sequence. X1 is kind of fixed, easy. X1 first 31 values are fixed. You can easily find out X1 sequence, any number of elements, by performing pre-order substitution. Sorry. What about X2? In order to calculate X2 sequence, you need CINIT, because first 31 values dependent on the CINIT. So the first thing we need to do is calculate CINIT. So to calculate CINIT, we have this formula that I have already showed you. 2 to the power of 11, I bar SSB plus 1, flooring value of N cell ID by 4, 2 power 6 I bar SSB plus 1 into N cell ID, percentile 4, which is basically giving you the modulo, the reminder. So this is the same CNIT formula that I have showed you, where in the PBCH DMRS case. So already these values I have decided, like where exactly I'm transmitting my PBCH DMRS. I already substituted those values earlier because I'm the transmitter, I'm the G node B. So obviously, once you calculate the CINIT value from that CINIT, so you can divide that into 31 bits and you can decide the first 31 bits. Once you have the first 31 bits, then you can calculate the X2 sequence up to 1768 numbers by using this pre-order substitution equation that is available. Because first 31 values available with the CINIT that we have calculated based on the configured values. So this is my X2 sequence. Once you have X1 and X2 sequences, you can generate the scrambling sequence. This scrambling sequence is of size 168 elements. From X1 sequence, X2 sequence, we have computed the scrambling sequence by substituting their last 168 values and performing modulo 2 between them. Once you have the scrambling sequence available, you use that scrambling sequence elements, 168 elements, 0th element and first element we use and calculate the first signal PBCH DMRS. First one, you calculate first bit. Second bit, like that, you calculate the QPSK symbols, 84 of them. So these QPSK symbols, 84 of them, would be transmitted exactly in the subframe index that I have decided in that particular subframe, in that particular SS block. These symbols would be transmitted, and these symbols will keep on getting changed based on your first half frame or second half frame or the SS block index, because those are the important inputs that are going in into this formula. So these block indexes and everything, they are going in as the input. So if these numbers change, if the SSPBCH block change, the CINIT changes. If CINIT changes, X2 sequence changes. If X2 sequence changes, your scrambling sequence changes, because all are interdependent. Based on CINIT, you compute the first 31 values of X2. If X2 sequence changes, irrespective of X1 fixed, C of n changes, because C of n is computed from X1, X2 modulo operation over here. In a simpler way of telling, that is this. The PBCH DMRS that is transmitted in this block, are different. In all these blocks are different DMRS transmitted. Because the DMRS that is transmitted in the corresponding block will have to kind of give a hint to the mobile equipment about the first 2 bits or 3 bits. In this case, first 3 bits. Because LMAX here is 8. We are transmitting the blocks 8 times in a burst. And we are using 8 element, 8 beams here. So PBCH elements are different. So mobile kind of estimate what is the block number. At least half of it, not full, only half. So mobile receives these symbols on these PBCH DMRS symbol positions and then detect what is the ISSB value, I bar SSB. From that, it will calculate ISSB and NHF. Okay, next. The next channel we have is PBCH, stands for Physical Broadcasting Channel. Which symbols PBCH occupies in our in our SSB block? That is again dependent on the DMRS symbol positions. As we have discussed, Once the V value is decided, NCLID, that V value, NCLID modulo 4 kind of determines V. Once you substitute V, you will be able to find out the positions of DMRS. Because mobile already have the NCLID from PSS, SSS operation, it kind of computes it, find out what are the positions DMRS occupies in these symbols. Once you identify DMRS, PBCH DMRS, you know the remaining symbols in those positions are left out for PBCH. So you know which symbols are carrying the PBCH data. Those symbols you have to decode and try to understand it as PBCH data. Mobile can decode all these symbols, find out ones and zeros present inside it by demodulating the symbols easily, by finding out what are the I plus JQ symbols present inside. But what channel those symbols belongs to, mobile should know. But there is kind of help available by fixing these rules and regulations. Okay, so mobile know what is the position of these PBCH symbols in the SSB block it has detected. So what does the mobile do? Next, go and deal with the PBCH channel. But PBCH data comes from the higher layer. Now the three channels we have studied are control channels of the physical layer. Their data kind of gets originated at the physical layer itself. It won't be coming from the higher layers. The one that we have discussed about PSS, SSS, and PBCH DMRS. Because it all depends on the configuration of the physical layer components, like NCell ID, the sector ID, group ID. It depends on that. The data that we are packing inside those channels is not carrying any meaningful data from the higher layers. But the first channel that we are studying, which is containing the meaningful data coming from the higher layer, is this PBCH, physical broadcasting channel. Its data comes from higher layer. Why? Because this PBCH carry some important system information that the mobile required to operate in the cell, called as MIB, Master Information Block. That Master Information Block is prepared by RRC protocol, and it will be sent through the other layers if required, like PDCP, RLC, MAC, and it comes down to the physical layer. So physical layer is kind of taking it as a transport block input that is coming from the higher layer, from the MAC layer. And that transport block input, it has to take and process it, as you can see it over here. But you remember our physical layer processing block we have studied for the other channels, like PDSCH? That is different, and this is different. If you observe, if you remember, compare. Actually, here some blocks are missing when it comes to this PBCH part. There are some blocks are missing. But first we see one by one what these blocks are, what happens as part of each block when the data comes from the higher layer. Data comes from higher layer. Exactly, it is 24 bits of data that arrives from the higher layer, which we are denoting here in this particular slide as A sequence. We are denoting here. A minus 1. A here is equal to 24. So it starts from A0 up to A24 minus 1, which is A23. We have bars, A bar 0 to A bar 23. These are the 24 bits of significant information that comes from the higher layer, which is master information block, which is kind of giving some crucial information about this cell to the mobile. Now, but for this 24 bits, physical layer will add some additional timing information, timing specific bits it will add. How many bits it will add? Another 8 bits it will add. So totally it will become 32. Actually, this is wrong. 32 it is. 8 bits it will add, not 31. A31, the sequence is up to 31. A0 to A31 is 32 bits. Should be 8 there, not 7. Actually, A plus 7 should be 32. A is 24. A bar is 24. Okay. What will be present in these 8 bits that are being added in the physical layer? In that, the first 4 bits out of these 8 bits that are getting added contains the least significant bits of SFN, system frame number. What is system frame number? You remember? In the time domain arrangements, we have divided the time into frames, radio frames, where radio frame size is 10 milliseconds. And every radio frame kind of have a number. Now you can see slowly network started feeding the information to the mobile. It is indirectly giving it information to the mobile that, hey, you are in so-and-so SFN, man. You are so-and-so frame number. Why network is giving these details to the mobile? What is the use of this information if you give it to the mobile? Mobile kind of, once it gets this information, says, okay, if in the future, if I was told by the network that in so-and-so radio frame, I am getting the resources, I know where that radio frame is, where that frame is, operating frame is, because I know the running frame numbers. Network is giving me the details. But remember, this PBCH payload, additional payload that is getting added, is only bringing you just 4 bits of SFN, not the entire SFN value, only LSB it is getting you. Oh, remaining another half you will have to get somewhere else. From where you will get it, we will see. But it is getting the first 4 least significant bits from here. Okay, next. 5th bit is about half frame information. It's called as a half frame bit. Either it is going to have 0 or 1. It is also kind of giving mobile equipment information about what is the half frame it is present in. Again, why it is getting repeated? It is already found out by the mobile. No, mobile found out only in case of L is equal to 4 case. If it is L greater than 4 case, mobile need it. That is why they are feeding that information in PBCH, that half frame data. Okay, so we have, what about the remaining 3 bits? Totally 8 bits. 4 plus 1, 5 gone. Remaining 3 depends on the LMAX value. LMAX value is 4 or 8 or 64. 10 and 20 used only for some special cases, which we can ignore. 4 or 8 or 64. If we take 4 or 8, that is only applicable for our 30 kilohertz scenario, operating band. So what are the cases? 5th bit is going to contain MSB of KSSB. What is KSSB? I'll introduce that later. SSB block, this is called as offset position, KSSB. What is it? I'll have to explain you in a diagram. I'll explain it. So it will carry the KSSB's MSB value, most significant bit. That will be placed here as the 5th bit. Next, 2 bits are reserved for future operation. If it is the other scenarios, you are going to get the other half of the MSB part of the block index. You got the LSB part of the block index already, 2 or 3 bits earlier, but now you are getting the other half here, especially when the L value is, Lmax value is very big, like 10, 20, 64. If it is 2 or 3 bits, it is already received by the mobile, 2 or 3 bits. If the number of times the block is sent only is 4, you can send it with 0001 1011. 2 bits is enough. When it is 8, 0002 111. 8 combinations finished. So with 2 or 3 bits that already mobile got in PBCH DMRS, mobile estimated what is the block number. You don't need this MSB part. MSB part is needed only when the number of SS blocks that are getting transmitted in the system are more than 8. If it is 10, 20 or 64, because you got only the first 2 or 3 bits from the previous operation, so you get the remaining things from here. The remaining block index. Okay. Fine. Let us go to the PBCH scrambling. Okay, now we know what data is added. So it is kind of adding frame number related details, which half frame it is in, and it is adding MSB of KSSB. That's the most important details from our 30 kilohertz point of view, our RIL band point of view. Okay. What kind of scrambling it will do? This PBCH is a special channel where they have decided to do scrambling 2 times, not 1 time. First time the scrambling is done by using this particular formula. S of I is equal to C of J plus Vm. V is kind of value of V comes from this table depending on the SFN values that you have decided to send for PBCH. System frame number values. Third LSB bit and second LSB of SFN, based on what they are, you decide the V value. That V value going here into this V position. The M value is dependent on this size. This A size is 24. So that becomes 24 minus 3, 24 minus 4, 24 minus 5, 24 minus 6, dependent on the Lmax value that you are operating. So you get this M value by substituting this A position 24 you substitute. Or 32 you substitute after adding the bits. It becomes 32. So 32 minus 3, 32 minus 4, 32 minus 5, 32 minus 6, or 31 minus actually. So once you have that, you have V of M. Your scrambling sequence, C of this C of J is typically scrambling sequence. And to generate this scrambling sequence, you have to use the C init value is equal to N cell ID. Whatever the scrambling sequence you want to generate, it directly N cell ID will be considered as C init. No big formula. Simply whatever the N cell ID operating on that cell, that you convert it into 31 ones and zeros, and that gives you C init, present 31 values of X2 sequence. From that, you can compute scrambling sequence. That scrambling sequence C of J would be cyclic shifted by VM units. For example, if M turned out to be 30, let us suppose V turned out to be 1. So the VM value will become 30. Now, if you substitute 30 in C of J plus Vm, if you wanted to find out the first bit here, you have to substitute 0 plus 30. That means the first SFI bit is the 30th bit of the scrambling code. So you're basically, to calculate SFI, you are cyclic rotating the scrambling sequence here. You are cyclic rotating it by 30 units based on the V and M. Because V and M turned out to be value 30, C of 30 is nothing but the 30th bit scrambling bit of scrambling sequence is becoming the first bit of SFI. Or it is the SFI value, basically. So to scramble different bits, you have to take a different A value. That by substituting that A value, you get M. By substituting that M plus this SFN related information that you decided to transmit this PBCH, where you decided to transmit this PBCH in which radio frame, that will derive your V. By substituting that V, you calculate the SFI. So SFI is the actual bit that you are going to you are going to take to substitute here into this modulo operation, so that your scrambled data comes out. EFI is the original data that is scrambled with this SFI. SFI calculated either it will be considered as 0. SFI is considered as 0 for payload generation bits. What is payload generation bits? The 8 bits that we have added in the previous step. For them, you don't need to do the scrambling. You will just use zeros in the SFI position. Those bits will stay as it is. But the 24 bits that have arrived from the higher layer, you calculate SFI from the scrambling sequence. SFI bit by substituting different V and M position values. So once you compute that, you have the scrambled PBCH data. How many bits are scrambled? Only 24 bits are scrambled out of 32. The remaining 8 bits, they did not get scrambled, because for them we have considered the SFI, the input as 0, SFI bits as 0. So they are as it is. They are not touched. So your data part is scrambled. Your payload generation bits that are added, 8 bits that we have seen in the previous slide, they did not get touched. Okay. Next. So we do all other operations like CRC, you attach 24-bit CRC. So already existing 32 bits, it will become 56 bits totally. So a sequence of up to size 55, 0 to 55, 56 bits. And that goes through channel coding. And after polar coding, channel coding bits are added. These 56 bits become 512 bits after channel coding. So a lot of metadata you add in order to provide security for this data. Even if some of the bits are corrupted while receiving, mobile equipment would be able to easily decode the data from that. So you're doing channel coding. And then these 511 12 bits that are available, after rate matching, they will become 864 bits. You add some padding bits there. Because for the available amount of PBCH symbols, you have actually 432 symbols available for PBCH operation. Again, from the same table that I showed you. So because you are using QPSK modulation for PBCH with lowest modulation, each and every symbol will be able to send 2 bits. So it can totally send 864 bits. But actual available data is only 512 bits. What do? As part of rate matching, you do the matching. So you added some dummy padding and made sure that it is perfectly fitting into the size that is available. Now, once this is done, now you perform scrambling for the second time. There is a 2-level scrambling that works for this PBCH data, but this time you scramble all the bits. So you take C in it, the X2 initializing condition to generate the scrambling sequence is NCell ID. From that, you get the first 31 values, compute CFI. Once the scrambling sequence is available, you take V and M bit. V is either the 2 least significant bits of the block index number or the 3 least significant bits of the block index number that you already have computed from, PBCH DMRS. Now, the point is, mobile, in order to decode PBCH, definitely need to already would have decoded PBCH DMRS, because only from PBCH DMRS you have these 2 bits or 3 bits available. The last 2 bits or last 3 bits available from the PBCH DMRS. So if you did not have decoded the PBCH DMRS, you couldn't decode this PBCH channel itself, because the PBCH scrambling is based on those bits. That's kind of playing a role as V here. And for the M number of bits that you wanted to compute, you take that M bit also, bit number also into this equation here, the bit number. And then from that, you do the cyclic shifting of this scrambling sequence. Remember, anytime you have a scrambling sequence which is containing an additional input, you have to consider that this scrambling sequence calculated will be cyclic shifted by this unit. For example, if V of M bit total value is 8, let us suppose, the scrambling will be 8 bit for 0th element. When I is 0, scrambling bit which we have to take is 8th bit, because this VM bit is 8, even though I is 0. For if you want to calculate bit tilde of 9, or second bit, if you wanted to calculate, so you put 1 here. B of I is only 1, first bit you take. But C of I, even though you put 1 here, this is already 8. So 1 into 8, 1 plus 8, it becomes 9. So scrambling bit, 9th bit you have to take. It's like that. So you have to kind of do the circular rotation. After you go to the last available size, it will come back to 0 once more, because we are using modulo operation. Okay. So the data is scrambled by using this scrambling sequence. Second time scrambling is occurring. And the modulation mapping we use for PBCH is QPSK. So M number of bits, which are 864, would get converted into 432 symbols placed onto 432 symbol positions. In the SS block. Now this is on the transmitter side. By receiving it, what the receiving end would be able to estimate that first of all, receiver can decode this PBCH only after decoding PBCH DMRS. But if by assuming that the PBCH DMRS is already decoded, mobile can easily decode PBCH because that is the only linking point. In the scrambling, we have used those bits that are learned from the PBCH DMRS. We have placed them there in the I equations. But after decoding and demodulating, mobile would be able to extract just 24 bits out of this QPSK operation for the higher layer and some additional 8 bits for your timing related information mobile would get. But once mobile gets the 24 bits, in the 24 bits, what details would be there? The details mobile find out from those 24 bits that is present in the PBCH is called as MIB, master information block. Once it decodes that, these details mobile will find totally. All of these elements size together is equal to 24 bits. For example, the system frame number is 6 bits. What is system frame number? Already we got system frame number. No, we got only 4-bit system frame number we added in the payload part. Another 6 bits is coming from here. So this 6 bits plus their 4 bits, total, your system frame number size is 10 bits. That 10 bits will give you the value ranging from 0 to 1023, 2 to the power of 10 minus 1. So that means PBCH part is divided into 2 parts. The data that is coming from the higher layer, adding the most significant bits, the MSB bits of the system frame number, which is the 6 bits, it is adding. The least 4 bits are added as part of the physical layer payload generation part. It is getting added. In the 24 bits, you are having only one half. Remaining half is coming from payload generation. But anyway, mobile will get everything after mobile downloading and decoding the PBCH. It gets all the symbols, 432 symbols. From that, it will extract 864 bits. It will throw the coding bits. It will remove the CRC. It will do all the things. Total number of bits that will be available for after extracting is 32 bits. In the 32 bits, mobile knows that 24 bits is the MIB that must be decoded by using these rules that are provided in RRC protocol, because this is RRC data. Of course, physical layer won't understand it. It will be sent to higher layer. Higher layer reads that information and send the information back to physical layer with the help of the SAP. So for this data, you have to be dependent on the RRC. These 24 bits, you have to send to RRC. RRC will kind of tell you back this information, these details. But ultimately, mobile gets this. But the remaining 8 bits, those are payload generation bits added by physical layer, GNODB's physical layer, and read by physical layer. Those 8 bits won't be sent to higher layer. So once mobile's physical layer extracted 32 bits from PBCH, it will only send 24 bits information to higher layer. 8 bits it will keep to itself, whatever that it has received in the form of payload generation bits that are arriving. But these 24 bits that are sent to RRC decodes it into these many details, totally 7 details it will decode that into. The system frame number, which is the MSB part of the system frame number, of 10-bit sequence number, system frame number, you got 6 bits there. And mobile would be given a hint about what is the SES operating here in this particular cell. If it is FR1, if the value is set to first field, SES 15 or 60, mobile understands that it is 15 kilohertz of carrier spacing. If the second field is set, mobile understands that it is 30 kilohertz of carrier spacing. But if it is FR2, If first field is received, mobile understands that it is 60 kilohertz spacing. If the second field is received, it understands that it is 120 kilohertz. So it depends on what is the operating band, FR1 or FR2. So if it is FR1, the options are 15 or 30. Otherwise, it is 60 or 120. Mobile is intelligent enough to detect which operating band it is working right now. So it can easily identify this value, either 15 or 60 or 30 or 120. Next, SSB subcarrier offset. This SSB subcarrier offset is called as KSSB. It is. If you remember, we already received some part of the KSSB earlier. You remember it is adding that KSSB as part of the payload generation bits. Some part MSB bit is getting added in the payload generation part, most significant bit. The remaining part you will get it here, the SSB subcarrier offset value ranging from 0 to 15. By combining these two things, mobile will get to understand something called as KSSB, whatever it is. What is it required for, where it is, what is KSSB, I'll tell you. But half part is arriving in payload generation bits, another half part is arriving in MIB. Also, mobile will get to know DMRS position in the dedicated channels, PDSCH, whether it is position 2 or 3. What is it at the time when we are studying that channel, we'll understand. And there is this PDCCH config SIB1. Mobile need to download some system information block called as SIB1. To download it, mobile would use this configuration details related to something called as control resource set 0 or core set 0. What is this core set 0 or what is it set space 0? What are these things? We'll learn later. We'll be introducing that control resource sets. But it is a set space on some channel called as PDCCH where mobile will have to look for SIB1. So SIB1 configuration details are coming. Only after knowing it, mobile would be able to kind of find out how the SIB1 is arriving. Whatever this is a system information block called as MIB, master information block, the primary detail, MIB. Now the cell is barred or not, intra-frequency reselection is allowed or not, etc. Other details are there. There is a spare that is left out for future operation. Right now it is useless. That means out of the 24 bits that the MIB is formed from, 1 bit is waste. 23 bits would be decomposed into these 7 parameters. When each parameter there is a size. Typically for the first field it is 6 bits. For the second one you require only 1 bit because either this or this it need to kind of report. So this will be represented with a bit 0. This is represented with bit 1. Ultimately it is 1 bit. SSB subcarrier offset, you require 4 bits because value is up to 15. So 4 bits are enough. 4 bits, 1111, it represents 15 in decimal in binary format. For this DMRS, 1 bit is enough. For PDCCH config, it is dependent on again these two things. Each one of them can take 4 bits. So if this is 4 bits, this is 4 bits. So you require 8 bits for PDCCH SIB1. So this is 1 bit, this is 1 bit, this is 1 bit. So if you count, so this is 6 bits, this is 1, 7, plus 4, 11, plus 1, 12, plus 8, this is 12 plus 8, 20, and this is 21, 22, and this is 23. One is missed somewhere. Maybe they must be using 1 bit for this structure forming for PDCCH because it is containing, it is not defined directly, these elements. These are present inside one other package. To represent that inside package, they might use 1 bit. So that will take 1 bit in the ASN.1 structure. So total, it becomes 24 bits of information. This thing is, it's all binary data, ones and zeros. But by decoding that ones and zeros, mobile will get this knowledge depending on what those corresponding bits are set to, zeros or ones. Okay. So to summarize the first half of our study today, we have completed how mobile equipment able to successfully find out this special block called as synchronization system block And from that, it will be able to detect what is the running frame number that is going on, and whether it is present in the first half of the block or the second half of the radio frame, and what is the radio frame number. Like that, various details it will get from these channels, and also required cell scrambling code, or PCI, or NCell ID, we call it as. You can extract that NCell ID from the information arrived from PSS, SSS. You can calculate by using the same NCell ID. You can decompose the PBCH DMRS to find out the information that is hidden inside, like the SSB details and NHF half frame related details. And as well, the same scrambling code is used for descrambling the PBCH as well. If you wanted to descramble any data, you require the scrambling code, because the same formulas would be used for scrambling on the receiving sending side as well as receiving side. But it is opposite operation on the receiving side. But after mobile successfully decoding this synchronization system block and reading it, it will be able to find out what is the SSB block number that is going on, what is its signal strength, and various crucial details about the cell, like the system frame number and so on and so forth, other technical parameters that are needed for mobile equipment's further operations. So those are extracted from this synchronization system block. It kind of can be placed anywhere in the band based on by following some rules. But wherever it is, mobile can find it out by scanning through the frequency and detecting this PSS, which is containing special modulated symbols, which are ones and minus ones. Okay. Any questions so far? Is this part clear? All right. Great. We take a break for 10 minutes. So we come back. We haven't yet completed all the downlink channels. We have completed only SSB block. We have the PDSCH, PDCCH, etc. So those things also we will study. Okay. So let's come back. At 11:05. Okay. Sorry, 12:10 we'll come back. Okay.